Okay, and welcome to our video on implicit differentiation examples. Okay, so there's big theory in the background here about the y actually being locally a function of x. We can see a little bit of the theory here with this. We need to slow down for a second. So what we have, the big story here in terms of these actual curves, we've got it's kind of a dictionary between algebra and geometry. So here's the algebra, here's the geometry. The algebra is solutions of an equation corresponding to points on a curve. And the idea is that when you write down an equation, if you plot all the solutions, you get a curve. And every point on this curve is a solution of this equation, and every solution of this equation, is a point on the curve. So for example, x equal to 0, y equal to 0 solves this because both sides will be 0, and so the point 0, 0 is plotted. Right, that's the first thing. Then the second thing is that locally, which means near a specific point, like for example here the point 2 root 2 over 3, which is like this point here, we get that, sorry, I didn't set my timer. Okay, the curve, it might be smooth, in which case we can talk about the tangent. So what does that mean? Well, smooth means if you zoom in close enough to the point, it looks like a line near there. Hopefully you can see that. And the line it looks like is what we call the tangent. Okay, so that's the first thing. And then the second bit of theory, which will be mentioned here, but you'll have to look at the previous lecture to kind of see a little bit more of it, is that this thing here you see, this curve, is not the graph of a function because, for example, at x equal to half, it's got two outputs. It's actually a couple of functions glued together. I can't see exactly here which are the two functions, to be honest with you, but it might be, I should be able to see it. I think the top, so from here to here, and here up, that's one function, and here to here and here down is another function. But the theory just says if you've got a point where it's smooth and the tangent is not vertical, like here, that if you zoom in close enough on the point, that the portion of the curve that you're zooming in on, which is a curve, is a segment of the graph of a function. So you can write y is equal to y of x. Okay. And this is what I do recommend you to do with these questions. How do you know it's implicit differentiation? Now, it doesn't actually have to mention it. Your exam or test, well, we won't worry about that. Usually it'll say, oh, use implicit differentiation. But if you've got an equation and it's talking about a curve, then you can always do this. This is what the implicit is. If you have an equation and it's a curve, it usually means, oh, well, the curve is all the solutions, etc. Okay, we won't do that anymore now. We'll just, the first thing you do with implicit differentiation is you replace the y with y of x. After a while, you don't have to do that, but I do recommend it. That's the first step. Okay. See, what we're not actually going to find y of x. In this question, you actually can, so it's not a great example, but anyway. What we're going to do now is we're going to differentiate both sides with respect to x. Now, there's two things to look out for here. The first thing is for a later section in this chapter, when you're differentiating a constant times a function, like 3 times this, you're going to fix the constant and then differentiate the function. That's the first thing to say. And the second thing to say is, on the right hand side here, I have a little product, things multiply together. So I'll need the product rule on the right hand side. You could multiply out the right hand side. I think you end up with x cubed minus 2x squared plus x. I'm not going to do that here. I'm just going to say, okay, this is going to be a product rule, u by v. So we're going to differentiate now both sides with respect to x. Okay, fix the constant 3. Maybe, okay, so 3. Now, differentiating y of x all squared. By the way, you could actually do this with a product rule because it's y by y. Okay. Now, the funny thing about this chain rule is we don't actually find out what y of x is. We just leave it as y. Okay. So the chain rule says you differentiate the outside. The outside function here is x squared. The derivative of x squared is 2x. The chain rule says differentiate the outside. We've done that. Then evaluate it at the inside. The inside here is y. You only write the y of x once. And then multiply by the derivative of what's inside. Now, you don't know what y of x is. So all you can say about the derivative of y of x is it's dy dx. And this dy dx is basically you just saying the derivative of y with respect to x. Okay. So this is the derivative of 3y of x squared. 3y squared. And this is where, like, you might say, oh, the derivative of 3y squared is 6y. Well, it depends. What does differentiate mean? The derivative of 3y squared with respect to y is 6y, but we're not differentiating with respect to y, we're differentiating with respect to x. This is why we have to be more careful. Now, on the right hand side, we have a little product. So you hopefully know your product rule. You do the first thing, which is x, times the derivative of the second thing. Now this second thing, to differentiate it, technically it also needs a chain rule. You got an inside function which is x minus 1 and an outside function which is x squared. So let's go away and use the the chain rule. So I'm differentiating this. I'll write the u and the v dash underneath afterwards. So the outside function here is x squared. The derivative of x squared is 2x. Evaluated at the inside is x minus 1. And then times the derivative of what's inside. And hopefully you know that the derivative of x minus 1 is 1. So that's the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing, and hopefully you know that the derivative of x is 1. And so what we're talking about here in terms of what the hell just happened, well, this is u by v, and the product rule says if you want to differentiate u by v, you do the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing. Okay, and now we're being asked to solve for dy dx, so we're not that far away. I mean, you could multiply out the right hand side, but there's no real need. To be honest with you, I mean, multiplying by 1 makes no difference. And here I've got 3 by 2 is 6y. I'm trying to find dy dx. All I really have to do at this point is divide both sides by 6y, because I'm just looking for dy dx. We might write down underneath what we actually did here. We applied a function actually, or an operator, which was the dx function. And we applied that operator to both sides. Okay, and now I'm going to want to get rid of this 6y, so I'm going to divide both sides by 6y, and I will end up with dy dx by 6y divided by 6y is just dy dx, and then here I'm going to write, okay, I'm going to write x by 2 is 2 by x minus 1 by 1 makes no difference, plus x minus 1 squared, and if I divide this by 6y, I get this. Happy days, that's dy dx. And as we said in the previous lecture, it depends on x and on y. Because these things aren't functions, it's not good enough just to specify the x, there could be two y values. Okay, that's part A done. Part B, hence find the equation of the tangent to the curve at a certain point. So the first thing to say is that, okay, the equation of a line is y minus y1 is equal to m times x minus x1, and we have an x1 and a y1, so that's no problem. The x1 and the y1 is the point that we're interested in here, that's no problem. The second thing is the slope. Now straight away, slope of tangent, you have to be, I'm saying slope of tangent, you have to be thinking already dy dx. This is the slope of the tangent. Okay, now we are interested in the slope of the tangent, dy dx, at this point. We're going to be substituting this into this. Now one thing we've got to say is, look at the picture, we're going to hope that this thing comes out positive, because this is a positive slope. Right, so m, slope of the tangent, is dy dx all day long, and this is why we differentiate. And we want to find this dy dx at this point 2 square root of 2 over 3. So I'm going to substitute x equal to 2 and y equal to square root of 2 over 3 into this. I would normally like a nice number. If this comes out a little bit messy, against my judgment, I will use the a 4 significant figure rounding. That's okay. Even though I really don't want to. Okay, so 2x is 2 times 2 times x minus 1 is 2 minus 1 plus 2 minus 1 squared divided by 6 times. So I really want to write this, well, this is fine. So the x's are 2 and then the y is root 2 over 3. And against my, what I want to do, I will do 4 significant figure rounding on this. Now the other thing that's probably worth saying at this point is careful what you're putting into the calculator. The more you press the calculator, the more likely you are to make a mistake. For me, you do not put 2 by 2 into the calculator, that's 4. You do not put 2 minus 1 into the calculator, that's 1. Multiplying by 1 makes no difference. And this is 2 minus 1, which is 1, and 1 squared is 1. So that's that. Divided by 6, I don't know, I presume you can see what I'm doing here. 6 by square root of 2 over 3. So this is what I'd like to use, but let's go with the 4 significant figure rounding, which is 1.02. Now it's 0.6, so this is first significant, second, third, fourth, and because this is bigger than 5 or bigger, you should round this. Okay, so we've got a slope, we got a point. We can now do our little equation here. I'm going to round root 2 over 3, well, probably at the end. Okay, so I have y minus y1. The y1 is the y point root 2 over 3 equal to the slope, which is 1.021 times x minus x1 x minus 2. Now I recommend you write these things as y equal to mx plus c. Looking back at the picture, this kind of explains why, because the c is where it cuts, so I'm going to expect my c to be between -1 and -1.5. I know my slope is positive. I've got that at 1.021. So what I'm going to do here is I'm going to multiply the right hand side out. So what I was mumbling there was that if you've got the equation of a line, the best way is to solve it for y as a multiple of x plus a constant, because then you can easily plot it. So 1.021 times x, and even I can multiply that by 2, 2.042. And now I want to add square root of 2 over 3 to both sides. Now there's approximations here already, but we'll just assume that's okay. So I got minus 2.042 plus the square root of 2, because I need to add this to both sides to get rid of it, and I get y is equal to, well, in my head approximately, but anyway, 1.021x minus 4 significant figures, 1, 2, 3, 4. The one after this 5 is 5, so that'll round up to 6, minus 1.226. And as we said, it is somewhere between -1 and -1.5. So that's that question done. Now we're going to do hopefully 2 more examples with probably a little less commentary on the theory. We're going to replace the y with y of x, and we're going to drive on. Okay, nice little example here of where these, like, why would an engineer care about this kind of thing? Usually it's when you're kind of getting to big specky design where you need to use kind of specific curves. I think in the first section in this chapter we saw the involute gear where the teeth followed a curve that was a parametric curve. Here's another example. You have windows on planes are what are called super ellipses because corners are not good for stresses, etc. That's enough of the spiel. Off we go. So, first things first, write y as a function of x. So you write y equal to y of x. So we have x to the power of 5 over 2 plus y of x to to the power of 5 over 2 equals to 1, step 1. The question is looking for us to use implicit differentiation to find dy dx, differentiate both sides with respect to x. Now we're going to be using the power rule that says when you differentiate a power of x, you multiply by the power and reduce the power by 1. Okay, so differentiate everything inside, well, both sides with respect to x. So we're applying the same function to both sides. We're calling an operator the ddx operator. Okay, so the derivative of x to the power of 5 over 2, well, we multiply by 5 over 2, then we reduce the power by 1. 5 over 2 is 2.5. Take away 1, you got 1.5, which is 3 over 2. Okay, plus, now this yoke. Now this, again, is a chain rule because I've got an outside, which is x to the power of 5 over 2, and an inside, which is y of x. So I need the chain rule. The chain rule says you differentiate the outside. What is the derivative of x to the power of 5 over 2? We've just done it. It's 5 over 2, x to the power of 3 over 2. The chain rule says you evaluate at the inside. Now, evaluate means put something here. The inside here means the y of x, but you only have to write this y of x once. Bang in the y there. Now you say, well, why don't you put y of x? Well, the y of x and the y are the same thing, so there's no problem putting that there. And then times the derivative of what's inside. What is the derivative of y with respect to x? The only way you can write that is by saying the derivative of y with respect to x equals to the derivative of 1, a derivative of constant of 0. Okay. So now what we want to do is solve this for dy dx. So the first thing that's in my way is this 5 over 2 x to the power of 3 over 2. It's added. The inverse of adding that is subtracting it. So I'm going to take away 5 over 2 x to the power of 3 over 2 from both sides. I'm also going to, oh no, that's all I'm going to do at the moment. So I end up with 5 over 2 y to the power of 3 over 2 times dy dx equals minus 5 over 2 x to the power of 3 over 2. And I'm looking for dy dx. It's multiplied by this. So the inverse of multiplying by this is dividing by this. Now this is a little bit more difficult now because they're not all numbers. So actually I'm going to have to do something else. Probably my best bet here is to I'm going to do two things at once. I'm going to divide both sides by 5 over 2, but I'm not going to write down exactly what that means. And then I'm going to divide both sides by y to the power of 3 over 2. Okay, so this is what I mean by not writing it down. If I divide both sides by 5 over 2, this is a multiple of 5 over 2. If you divide by 5 over 2, it's gone. And this is also a multiple of 5 over 2. So if you divide by 5 over 2, that's gone. So this is where I am. So dividing both sides by 5 over 2, they're gone. That's good. And now the only thing that's multiplying dy dx is y to the power of 3 over 2. And it's easier to divide both sides by that. So otherwise you could end up with 5 over 2 times x to the power of 3 over 2 divided by 5 over 2 times y to the power of 3 over 2. It's a little bit messy. It's a bit easier to think like this. Divide both sides by y to the power of 3 over 2. You end up with dy dx equal to minus x to the power of 3 over 2 divided by y to the power of 3 over 2. Where the 5 over 2s, well, I already said that. If you divide both sides by 5 over 2, they're gone. Okay, so that's that question done. Use use implicit differentiation to find that. Okay, we've done that. Find the equation of the tangent to the curve at this specific point. So again, if we have a curve there, we may as well use it. So it's somehow symmetric in the x and the y. So it's probably here, and we're saying, okay, this is some kind of smooth curve. So let's draw our tangent. The slope we get out should be negative. We don't actually, well, this is 1, but we won't worry about that so much. Okay, so let's see. So I suppose I want to find the equation of the tangent. The tangent, first of all, is a line. So when you see line, you're thinking y minus y1 equals m times x minus x1. You do in fact know x1 and y1 because you have a point, this 0.7579, the 0.7579, which is presumably a solution of this equation because it's a point on the curve. And the thing you're missing is slope. Now I'm going to say these words and you should already be thinking slope of the tangent. Slope of the tangent, you are thinking dy dx. So if I evaluate this at the point 0.7579, 0.7579, that is the slope. So we'll take this over the side here and say that the slope is equal to dy dx evaluated at this point. Now, if you look at it, you're going to have the same number divided by itself, which is 1. You're going to have minus 1, but let's slow it down. 0.7579. I forgot my minus. It's power of 3 over 2 divided by 0.7579 to the power of 3 over 2. You can put this into the calculator, but look, anything divided by itself is 1, so it's going to be minus 1. And the x1 and the y1 are those things. So I got y minus 0.75. No, I've written in. Excuse me, that should be 79. 7579 here equals m is minus 1 times x minus 0.7579. So as before, I recommend you solve this for y equal to mx plus c. So multiply out the right hand side. Minus 1 times x is minus x. Minus 1 times minus 0.7579 is plus 0.7579, and then just add this to both sides. Oh dear. 0.7579 plus itself is 1.5158. I'll go to 4 significant figures, so this is an approximation. 1.516. And that makes sense because you've got the slope is negative, it's minus 1, it's going down, and trust me, this point is actually x equal to 0, y equal to 1, so it's going to cut kind of at 1.5, and that's what we have there. Okay, one more example here. Right, so yeah, we will get cracking. So again, this is looking at the point 1, 1. I'll probably do this one a bit faster because I'm a little short on time for the video. So this is 1, 1. We're going to find dy dx. The reason we find dy dx is because we want to find, now actually if I plot this more accurately, I can estimate my c a lot better. So I'm going to predict the c getting quite close to 1/2. Now if I've drawn it slightly off, it could be like 0.4, point whatever, 0.6, we'll see. So this is the point 1, 1. We want to find dy dx first, and then what we're going to do is we are going to find the equation of this tangent line. The slope is going to be positive, it's going to cut somewhere near 1/2. Okay, so first off, write this, and I'll do it up here, as y of x squared times 1 plus x. You could multiply that out, by the way, but no harm in you seeing product rules. So I'm going to go fast. Remember, you can pause me. So I'm going to differentiate both sides with respect to x here. This y squared is multiplied by 1 plus x, so automatically that gives me a product rule. The product rule says, now by the way, there's one thing, I don't want dy dx is equal to here, I differentiate both sides. So anyway, product rule So it's the first thing, which is y of x squared. Now I only really ever have to write the y of x once, so I'm not going to write y of x squared, I'm going to write y squared. Times the derivative of 1 plus x. You should know the derivative of 1 plus x is just 1. Plus the second thing, which is 1 plus x, times the derivative of y of x squared. And this is where we can slow down. Y of x all squared has an outside, which is x squared, and an inside, which is y of x. It needs the chain rule. The chain rule says you differentiate the outside. The outside, function here is x squared. The derivative of x squared is 2x. But the chain rule says you evaluate at the inside, which is y. But you must multiply by the derivative of what's inside. We do not know what y of x is, but we can say that its derivative is dy dx. So we've differentiated this using the product rule. Plus the derivative of x cubed is 3x squared. There's no need for any chain rules or anything because this is a function of x. See, this is a function of x, but it's got an outside and an inside. Minus, remember, fix these constants, minus 3, and the derivative of x squared is 2x. And the derivative of 0 is 0. So you got a little equation to solve here in dy dx. It's not too bad. If you're solving for dy dx here, you want to get rid of this y squared, this 3x squared, and this 6x. So you will get rid of these things. The plus y squared, you get rid of it by taking away y squared. The plus 3x squared, you get rid of it by taking away 3x squared. And the minus 6x you'll get rid of by adding 6x. So you end up with 1 plus x times 2y, which for no particular reason I'm going to write as 2y times 1 plus x. Apologies about the speed now, I've only got about 28 minutes on the clock, as it were. So I have 6x here, I've added that to both sides, taking away y squared, taking away 3x squared. And to get dy dx on its own, I need to divide both sides by 2y times 1 plus x. Hopefully you don't run out of time here. Okay, so that's dy dx done. Okay, next thing is find the equation of the tangent line. Okay, straight away you're thinking y minus y1 is equal to m times x minus x1. When I say slope of tangent, slope of tangent, slope of tangent all day long, you need to be thinking dy dx. And we are interested in this at the point x equal to 1, y equal to 1. So I'm going to substitute x equal to 1, y equal to 1 into that. I'm going to go a little bit fast. 6 times 1 is 6. Minus 1 squared is minus 1. Minus 3 times 1 squared is minus 3. And on the bottom, I just go a bit faster again. 2 by 1 is 2, 1 plus 1 is 2, so 2 by 2 is 4. I'm seeing 6 minus 4 is 2 over 4, this is 1/2. And here you see that the slope is positive, that's good. And finally, y minus y1, y1 is 1, because that's the point we have, 1, 1, equal to the slope, which is 1/2, x minus x1, and the x coordinate is 1. If you multiply out the right hand side, you get 1/2 x minus 1/2 and add the 1 to both sides, and you get y is equal to 1/2 x plus 1/2. If you look at the picture, it's dead right, it's cutting at 1/2. Happy days.